Right, okay, so we've got normalised floating point number. That's the number. Stored using 4 bits for the mantis and 4 bits for the exponent. Both in 2's complement. Convert this number to denary. So we're just going backwards. This is the easy bit. Remember? Right, so to help me, I'm not going to try and work from that. I'm going to write the number out first. So I'm going to put 0, and I'm going to put my implied binary point in because it's normalized. And then I'm going to write out the exponent bit. Right, okay, so with all of these, work your exponent out first. So we've got, this is the exponent, it's negative, I don't know what it is, I do know what it is, but I don't, I'm going to assume I don't. So, don't know what the exponent is, so I'm going to do 2's complement. So flip, that's the last one, so flip, 1, 0. So the exponent is plus 2, which means this number is going to get bigger. So we know now what we need to do with the binary point. So we're going to move it 2 to the right to make it bigger. So the binary point is going to end up there. So that's a bit messy now, so I'm going to write that number out again. Put some column headings on so we can read it. There's no point in putting a column heading there. So it's 1, 2, 4. Oh, I'll put the half on, doesn't really matter. I'm converting it to denary. Okay, so that becomes 2. Again, it's about clarity, but it's the process. Everything always starts with, the first thing we're really going to do is work out what the exponent is. Always. Even when you do, yeah, go on.
Marx says the exponent is -2, and the point is moved 2 places to the left.
Yeah.
So, would the answer not be 1, 8?
What did I do? I made a critical mistake, a common critical mistake with 2's complement.
You forgot that it was negative.
What should I do? When I'm doing that, what should I do?
Write down negative.
Yeah, remember, I've said that to you. So I should say, I don't know what it is, but I know it's negative. That was +2, yeah. But that should have been -2. Right, so let's assume I did that and I've gone back and I'm going to check. What I'm not going to do is scribble all this through. Okay? I've got to this point. So I'm going to say, right, okay, now, sorry, the exponent was -2. Write out this number again. So we had 0.100. Right. I need to make it smaller. That's what negative means. So the binary point's got to go that way. So what I need to do is what Lucy asked before. I need to sign extend. I don't know how many. It doesn't really matter. I'm just going to put a load of sign bits on the front. Because now I'm going to move it that way. 1, 2. And I'm going to put it there. Now that I've done that, I'm going to write that number out again. So 0.001, it's got 0, 0. And then I can put some column ends in. So we've got 1 and 2, but then we've got half, quarter, and an 8. Okay? Because they said denary, it's not wrong to do that. Don't try and work it out. What is an 8?
0.125.
But you're not expected to. Just leave it as a fraction. It's easier to just leave it as a fraction. But if you do make that mistake, but that's why I made that mistake. I didn't write down that, right, remember, it was a minus number to start with. Easy to make that mistake. Okay? Right. And then the last bit. If you get asked anything like this, give yourself an example. Okay? Right. What does the number of bits in the mantissa affect? Well, the more bits we've got, the more close we can get to the actual number we want to store, the detail of the number, the fraction. Okay? So that's going to affect the precision, which is why we call 32-bit numbers single precision floating point because you've got 23 bits for the mantissa. And then you've got double precision, which uses, I can't remember how it uses now, 50 odd bits for the mantissa. We call it double precision. They did accept accuracy, but remember, accuracy is an effect that we see when we work with floating point numbers. The precision affects accuracy. Precision is not the same. Right, and then the exponent, well, that affects how much we can shift. So that's the range, isn't it? The size of the number. What's interesting, in 32-bit format, we use 8 bits for the exponent, but in double precision, we only use 10. So you can actually get quite a big range anyway. 2 to the power, I don't know, 1024 is quite a big number. We do have a quad precision, and there are other crazy number formats above that. Right, so takeaway there. These aren't hard questions, but they are easy to mess up. Okay, there's slightly a bit of a difference between 2 and an 8. Big difference. Wait, it's 4 binary points, isn't it? Because that's the equivalent of shifting left and right by those 2 much. Right, okay, I'll start that one there.